talk about the clear air turbulence and the Richardson number. So here we are using two colors to represent the fluid, the less dense fluid on the top and the denser fluid on the bottom. So this is a stable configuration considering this layer is lighter than this layer, right? So when we have a very stable situation like what we have in here, this is statically stable, wind shear can generate turbulence. It can still generate turbulence. So if we have very strong wind in between, so in the less dense layer we have the wind blowing in this direction, and in the less dense fluid the wind is blowing in this direction. And after a while what we can see is this: we have a lot of mixing. Even though this is very stable, how does that happen? So first of all, we have laminar flow, which means that there is no vertical components in this shear, okay? And then when a critical value is reached, we will talk about this Richardson number in the next section, okay? It's dynamically unstable, dynamically versus the term statically. So here is dynamically unstable waves form on the surface. Okay, we have some waves, and then we have some larger waves. And then after that, the amplitude of the waves grow. Each wave begins to roll up. So we can see there is a little rolling up of the wave, and the breaking wave is called Kelvin-Helmholtz wave. It's what we have in here. So this whole paragraph is describing only this one, okay? And in each wave, some lighter fluid is rolled under the denser fluid. So you can see that the denser fluid is rolled above some of the lighter fluid here, which means that there is a statically unstable situation in this rolling of the fluid. So it's creating static instability. Okay, and then after that we have the static and dynamical instability and causing more turbulent flows in here in all the rolling of this fluid. And then turbulence spreads and causing diffusion. So here is the diffusion, and it reduces the shear and static stability. So this static stability is gone because of all the mixing, and also the shear is gone, the wind shear is gone, and the turbulence decays without continued forcing. So if there is no continued forcing, this is the aftermath of all the mixing in this Kelvin-Helmholtz instability. And we can see this in the lab. So here is the lab, and then we can see this in the nature. This is the clouds. So it's creating by the strong shear in between the two layers, and we can also see that from the top in here. So this is one of the example when we want to compare the contribution of the buoyant production in the TKE and the shear production. In here is a mixture of, first of all, it's shear production, and then after a while it's shear production plus the buoyant production. This is buoyant production, right? Okay, so how do we make use of the Richardson number? This is what we call the flux Richardson number. On the top we have the third term from the TKE budget equation, which is telling us the buoyant production or consumption depending on the sign of this or the sign of this actually. And here is the shear production due to the shear of, obviously. This is the shear and this is the shear. So other terms are also important, but these two terms are simplified in here, are put in here so that we can examine the physics because these two are the two mechanisms generating turbulence. By the ratio of these two terms, negative sign is dropped by convention. So there's a negative sign in here, but we drop that by convention. Okay, and then all the assumptions still stand. And here the shear production is always positive, this whole term including this negative sign, which means that the denominator in here is always negative because of the negative sign in here. Okay, so for the statically unstable condition, the buoyant production is positive. So the top here is positive and this one is always negative. So we have negative for this flux Richardson number when we are looking at the statically unstable condition. If it's neutral, then there's no heat flux, then the term is zero. And when it's statically stable, the buoyant consumption is negative because we have negative heat flux. And the flux Richardson number will be positive because this is always negative. Okay, so the critical value 1 is telling us that the contribution from the buoyancy and the shear production is around the same. So these two terms are compared with each other because they are from the two main mechanisms of the turbulence generation. So here is a rather busy graph. So it's still talking about the Richardson number in here. We're comparing the contribution of the shear production, which is this one, to the buoyant production. So here is the third term over the negative fourth term, because we have negative in here. In here we have the positive shear production, and then we have the positive buoyant production over this side, and then the negative buoyant production or buoyant consumption over this side. So on this line, it's telling us that the condition is very, very stable, statically stable, and there's no turbulence in this zone. Until we are increasing the shear production, we are entering into the range where shear production is as strong as this one, is as strong as the buoyant consumption. And then after that, over this zone, the shear production is stronger. We start to have some turbulence here. It's stably stratified turbulence. It's I would say it's a weaker turbulence. And here we have zero buoyant production or consumption, but we have a lot of shear production. So this is mainly due to the shear production. The TKE generation is mainly due to shear production. So we call this forced convection. It's not free convection. Okay, and then after that, this zone is where we have both we have turbulence generated by both shear and buoyancy, because this side we have a statically unstable condition in here. Okay, and then after that we have very little shear production because we are staying in this range, little shear production, but the buoyant production is strong. It's called free convection because it's free from the it's getting the energy from the thermals, so we call this free convection. Okay, so here we have the flux Richardson number. We have already covered this. So for the turbulent flow, we have the turbulent fluxes, right? If we are having the turbulent flow, this is the turbulent part, and this is the laminar flow. So if we have laminar flow, we cannot calculate anything with these two covariances because we still don't have the turbulent terms yet, right? so we cannot make use of this Richardson number. So that's why we have to come up with another Richardson number, which is called the gradient Richardson number. We turn the covariance in here and in here, the covariances in these two terms, we turn that into the gradient of the mean wind in here and in here too. So by doing that, we are assuming that, for example, the gradient of the mean wind is proportional to the negative covariance. So this makes sense because if you have a profile looking like this, the U wind is increasing with height, right? Which means that the higher wind, the higher velocity wind is transferring its component downward to the lower, to the weaker wind, right? This is stronger wind and transporting its momentum to the part where we have weaker wind. So the transport is pointing downward, which means that it's opposite in the signs. We have to put a minus here, okay? It's called down gradient. Okay, last time we have covered this, the gradient Richardson number. We use this to define the top of the PBL. If this is a larger number, which means that it's a very stable situation. So this is the part where we have no turbulence or less turbulence. So the laminar flow becomes turbulent when the Richardson number is less than a critical value, which is 0.2 something. So you can see that the region in here, the laminar flow will become turbulent, or in here, okay. The turbulent flow becomes laminar when it's larger than 1.0. So even if you have turbulent flow, if your Richardson number is very large, or gradient Richardson number is very large, like the region here, then the turbulent flow becomes laminar, then there's very little turbulence happening in this zone. Okay, what if the gradient Richardson number is between 0.2 something to 1? Then it depends on the history of the flow. So if the flow was originally laminar, then it would keep being laminar. If the flow was originally turbulent, then it would be turbulent even though the gradient Richardson number is between these two values. It depends on the history, or depends on the last time steps. Okay, I have a question for you here. I have separated the zones into 5 different zones, and you should be able to tell me if it's laminar, turbulent, or you can't tell. Okay, so here is a question asking you about the dissipation of TKE. So let's say if the TKE can be expressed, the dissipation of the TKE can be expressed in terms of TKE itself, which means that if we have stronger TKE, then we have higher dissipation. And this L is actually the dissipation length scale, is like a reference value. And sometimes we assume that this value can be expressed in terms of the height in a neutral conditions. So you might want to focus on the middle graph in here. And if the TKE shown in figure B is assumed as the initial condition, so this one is the initial condition. There's no shear or buoyancy production or loss, so we can safely assume that the two terms which could generate turbulence are 0. No redistribution or turbulent transport, so all other terms are 0. Then at C equals to 100 meter, you have to find out the numbers in here according to the height and what is the initial value of dissipation rate. And then you will have to do a little bit of the calculus to find out how much time does it take for the TKE to reduce to 10% of its initial value. You have already found this initial value in the graph. Okay,